Okay, so we need to learn how to write Lewis structures for covalent compounds. We've been looking at the diatomic elements and water, but we can draw Lewis structures for a whole bunch of different compounds. So here are the steps. The first thing to do is to write the correct skeletal structure. That means connect the atoms in the correct way. So this skeletal structure just shows the positions of the atoms. This is a little bit like balancing chemical equations. I can't give you a hard and fast set of rules. I can just give you some guidelines. One of the guidelines is that hydrogen atoms are always terminal atoms. Terminal means they're at the end. They're not in the middle. Because hydrogen only has one electron, it can only form one bond. So it can only be attached to one other atom. It can't be between two atoms. It just doesn't have enough electrons. Another thing to keep in mind is that many molecules tend to be symmetrical. We are going to stay in the easy realm of drawing Lewis structures. In Chem 1A and in OChem, you get into more complicated stuff. We're going to try to stick to the more straightforward stuff. So they tend to be symmetrical. So if you've got lots of, if like BCl3, you got one boron and 3 chlorines. Well, the symmetrical thing would be to put the boron in the middle and put the 3 chlorines around it. We're going to see that happen a lot. The next step is to figure out how many valence electrons do you have for all those atoms. You look at the periodic table and you identify what group number they're in and how many of them you have, and you just get a total number of valence electrons. If you have an ion, then you have to adjust the number of valence electrons. And these ions are going to be those polyatomic ions. If you have a negative charge, you're going to have to add an electron. If you have a positive charge, you have to subtract an electron. Then we take our number of valence electrons, and those are going to be dots, and we start spreading them around. We're trying to get everybody happy. And this is one situation where we can make everyone happy because we're only going to choose molecules where we can do that. So you want to give duets to hydrogen and octets to everybody else. You have to have bonds or it's not a molecule. So start out by putting 2 electrons between each pair of atoms. That's the minimum number of bonding electrons. And then however many electrons you have left, start passing those around. If you don't have enough electrons to give an octet to everybody, you can't go to the bank and borrow some. You have to start doing more sharing. And so you're going to make double or triple bonds, take some lone pairs and move them into the bonding positions. So that probably didn't make a whole lot of sense. Let's do some examples. Okay, Lewis structure for carbon monoxide. Well, this molecule only has 2 atoms. So they must be connected to each other. So that makes the skeleton pretty easy. We're going to have the carbon connected to the oxygen. How many valence electrons does this compound have? Well, how many valence electrons does the one carbon atom have? It has 4. And how many valence electrons does oxygen have? 6. And 4 plus 6 is 10. So we can put 10 dots in our diagram. There's no charge, so we don't have to mess with that. So we have to start out with a bond between those. So there's 2 electrons. I'm going to draw the 2 electrons and connect the dots. So there's my bond. I have to have bonds, otherwise it's going to fall apart. So I've used up 2 electrons. Counting by 2 is a great skill here. So there's 2, 4, 6, 8, 10. You don't have to do it that way, but I kind of like to just, start spreading it out instead of just getting one all fixed up and then moving over. I ran out of electrons. I used up all 10. Do carbon and oxygen each have an octet? No, they don't. So what we need to do is they need to share more. So what we're going to do is we're going to take one of these lone pairs and move it, and it's going to become a bonding pair. So I'm going to erase that, and I'm going to put it in here, and that's going to make another bond. So now I have a double bond. So this oxygen is happy now, 2, 4, 6, 8. But the carbon has 2, 4, 6. So we're getting closer. We need to share some more. I'm going to take a lone pair from oxygen now and move that into a bonding position. So I'm going to get rid of this one and stick these in between and connect those dots. If you start out this way with, making the dots and then connecting them, it's easier to, get used to the idea that the line is 2 electrons. Now the carbon, 2, 4, 6, 8. The oxygen, 2, 4, 6, 8. There are 3 bonding pairs, and each atom has 1 lone pair. Now that's kind of messy, isn't it? You're going to make some messes when you're doing Lewis structures. So go ahead and make your little scribbly mess and then draw it up nice. So there's carbon, and we have a triple bond with the oxygen, and then there's a lone pair on each of them. Any questions? Let's do another one. H2CO. I'm going to tell you that carbon is the central atom. So carbon is the central atom. So I'm going to put carbon in the middle, and I'm going to put the oxygens and the hydrogens around it. And then I'm going to count electrons. So each hydrogen has 1 valence electron, and there's 2 of those. And the carbon has 4 valence electrons, and the oxygen has 6. So now we've got 12. So I have 12 dots. We're going to start out by making bonds. So there's 2, 4, 6. I'm going to put lines there. And now I've got some others that I can spread around. I've got 6 more, right? So I could do 2 there and 4, 6. So I've got 2, 4, 6, 8, 10, 12. 12 electrons, 12 dots. Why didn't I put any lone pairs on the hydrogen? Hydrogen's too small. Hydrogen never ever has lone pairs. He's happy with the 1 bond. Is this a good Lewis structure? Do carbon and oxygen have octets? No. Carbon does, but oxygen doesn't. We've got to make everybody happy. So if I took a lone pair from the oxygen and shared it in here, would that work? No, it wouldn't. Let's try it anyway. Now what's wrong? Well, the oxygen still has 6 electrons, right? This oxygen still has the 2, 4, 6, and now the carbon has 10. Does that make it extra happy? No, it makes it unhappy. Too much of a good thing, exactly. So we got to move these over. By putting 2 lone pairs on oxygen and a double bond here, this oxygen has 2, 4, 6, 8. The carbon has 2, 4, 6, 8. Each of the hydrogens has 2. Octet rule is satisfied. And then we'll draw it a little more nicely. H, C, double bond to the O, H there, and then lone pairs on the oxygen. That's a good Lewis structure for that compound. Any questions? So we can draw Lewis structures for polyatomic ions. I know some of you have been kind of wondering, well, why is nitrate NO3 minus? Why do they stick together? Well, to satisfy the octet rule is how they stick together. When we're doing polyatomic ions, it's the same process, you just have to be careful about the charge. And it involves a negative, and negatives always are confusing because they're backwards. If you have a negative charge, that means you gained electrons, right? Seems counterintuitive. If you have a positive charge, it means you lost electrons. So we do the Lewis structure, then we put brackets around it and put the charge on the outside. Let's do one. What's the name of this ion? Cyanide. So we're going to draw a Lewis structure for cyanide. That was too fat. That was a fat carbon. So there's the carbon and the nitrogen, 2 atoms. You can't get a much simpler molecule than that, right? They have to be connected to each other. How many electrons? How many valence electrons does carbon have? 4. How many does nitrogen have? 5. What do we do with this charge, -1? We add an electron. Electrons have negative charges, right? To get a negative charge on the overall ion, we have to add an electron. Now, it did not pick that up on the side of the road. It got that from a metal, but we're just looking at the ion by itself. So there's a total of 10. So again, we're going to put 2 between for a bond. So there's 2, 4, 6, 8, 10. What do we have to do? Yeah, we need to make them share some more. It's like, good job sharing that 1 pair of electrons, but we need you to share more. So let's take, I don't know, let's take 1 from the nitrogen. So we'll take this pair and move it. And when it's shared, it becomes a bond, so I connect the dots. Now the nitrogen still has 6 valence electrons, but the oxygen isn't there. There's no oxygen. The carbon has 8. It's too early. Yeah, 1:30 in the afternoon. I'm not ready to be up yet. So we're making progress, but this nitrogen is still not happy. So carbon needs to take 1 of its lone pairs and share. So we take a lone pair. I'm going to put that in here and share some more. Now, carbon has 6 from the bonding electrons, and 2 is 8, and nitrogen has 6, and 2 is 8. To finish it off, we need to put brackets on it and indicate the charge. Because if you had a compound between carbon and nitrogen, a neutral compound, that would be an incorrect Lewis structure because it's got the wrong number of electrons. Then, of course, we can clean this up and make it look nicer. Put brackets around it and the charge on the outside. Cyanide. Any questions? What's the name of that ion? ClO minus. Hypochlorite. Well, we got chlorine, we got oxygen. How many valence electrons does chlorine have? 7. And oxygen has 6. And it's got a -1 charge, so we need to add 1. So we've got a total of 14 electrons now. So we're going to put 2 there to bond them together, and then we'll start spreading the joy. So there's 2, 4, 6, 8, 10, 12, 14. I used up all my electrons. Is everybody happy? Yes. Trick question. Everybody meaning the chlorine and the oxygen. Not everybody in the room. That would be impossible. And then I'm going to put brackets and a charge on the outside. Any questions? This is something you have to practice. A good way to practice is to go on YouTube after I post this lecture and watch the video and then stop and do it yourself and then let the video go and see if you got it right. Exceptions. Every rule has to have an exception, right? So there are exceptions to the octet rule. It's a really useful rule, but there are exceptions. We're just going to talk about them. We're not actually I'm not going to test you on them. So there are some molecules that it's impossible to write a good Lewis structure for, and yet they actually exist. One of the situations is if you have an odd number of electrons. So if we look at nitrogen monoxide, the nitrogen has 5 valence electrons, oxygen has 6. 5 plus 6 is 11. You cannot distribute them in a way that everybody's got 8. It just can't happen. In situations like this, we just do the best that we can. So we could do it like this, or we could do it like, those are the same. I don't know. Anyway, yeah, those are the same. That's the best we can do. It's just like that. Another exception is boron. Boron is one of those little guys. He's element number 5. Lithium and beryllium, lithium especially is a metal, and so it's going to form ions, and so we're not going to run into too much trouble with him. Beryllium's kind of weird, and boron is also one of the little guys. So boron will often be satisfied with 6 electrons. How annoying is that? So we'll see boron trifluoride will do this, and the boron will have 6 valence electrons instead of 8, or boron trihydride. So just know that exceptions exist. If you happen to see one in a homework assignment or something, don't freak out. Other exceptions, we can have more than 8 electrons around a central atom if the central atom is big enough. We go into this in a lot more detail in Chem 1A. But elements in this third period, like phosphorus and sulfur, can do this. They do it by expanding into the d orbitals. But here, the sulfur has 2, 4, 6, 8, 10, 12 electrons, and the phosphorus here has 10 valence electrons. And these are real compounds, and that is how they are put together. Well, silicon, phosphorus, sulfur, chlorine, they can all do expanded octets, and anything bigger, like selenium, bromine, iodine. But you're never going to see an expanded octet for carbon, nitrogen, oxygen, or fluorine. So we do have these, unfortunate exceptions, but it's still a very good model. Lewis theory is a very good model of bonding and still very useful.